So today I'm going to talk about our new proposal, MPI+X stream, as explicit solutions to solve the performance challenges for MPI+X. We'll cover both the MPI+THREAD and the MPI+GPU. I first will talk about the performance challenges. We'll look at the performance challenge of MPI+THREAD and MPI+GPU. Then we'll visit two important backgrounds that lead to our proposal. First background is the endpoints proposal. And next, we'll look at the implicit solutions that for MPI+THREAD, which is currently adopted by most major MPI implementations. Then we'll go through the MPI+X stream proposals in details. Lastly, we'll look at some performance numbers adopting the MPI+X stream, and then look at some code examples to see how our proposal is being used in actual code. So let's look at the performance challenge for MPI+THREAD. With MPI+THREAD, the issue is that we have a very miserable performance in small message rates with the MPI+THREAD multiple. As we've seen in the lower left graph, when we send in small messages, in here is 8 bytes small messages, from using a single thread, the first dot, we actually have quite reasonable message rates. But as soon as we start sending small messages concurrently in more than one thread, the total message rates start to drop significantly, and it keeps going lower as we add in more threads. And the reason behind this is shown in the upper left diagram. And the main problem is MPI does not recognize the thread context, and nobody can tell MPI about it. And so when multiple threads concurrently entering MPI, then contend on the global lock, and not only they serialize all the communication traffic, they also add on to the latency when they're contending on the lock. So this is a pity, even though modern network hardware are capable of supporting multiple network endpoints underneath, and each network endpoints are able to deliver traffic concurrently, but we are not utilizing the hardware as we wish. So how is HPC applications for so many years are dealing with this? So they are dealing with it by working around the issue. So the first try, this is sometimes they get to us and we give them the advice, try avoid MPI+THREAD multiple if you can. And if you can't, try avoid calling MPI within your parallel regions. And if you can't do that, try avoid small message, try avoid your latency sensitive programming patterns. Unfortunately, what if these workarounds are getting less and less acceptable with modern trends in HPC? Literally, the nodes are getting fatter, and the system is getting more heterogeneous, and the programming pattern is getting beyond bulk synchronous parallel. For example, list a few. There's a data parallel, task parallel, and the pattern often involve event dispatching. And events are usually small messages and latency sensitive. Now let's switch gear and look at another performance challenge which is more relevant today with MPI+GPU. So it's a kind of a different challenge from MPI+THREAD, but it does share some of the common characteristics. So similarly to the one I referred to MPI+THREAD, in here MPI also does not recognize the new context. In here is the accelerator offloading context. So because MPI doesn't recognize it, just by using MPI forces the use of heavy synchronization between the kernel launching. And if we think about this accelerator, it has a very fast moving train. So the heavy synchronization is as if we are bringing this train slow down to all the way a complete stop, then trying to re-accelerate the train back up to speed. And without saying, this brings a great penalty for the performance. So for the solution, we need to somehow get MPI onto the train beforehand, and which is to allow MPI to be able to asynchronously launch the MPI communication and use the lightweight synchronization method, for example, via triggered operations. And for this solution to work, we would require some explicit way to explicitly input the GPU context into the MPI. If the implementation doesn't know about it, implementation can do nothing about it. So what is the common behind these two MPI+X challenges? So the common thing is the X here, they all brings in new execution contexts beyond what's in the standard is all about MPI processes. So for example, in MPI+THREAD, we have threads. And for MPI+GPU, we have the GPU streams and GPU graphs. And they all, they have the character, for example, threads are serial context within the threads and have a concurrent execution context between the threads. And similarly with the stream, it's also serial within and concurrent between. And in addition, GPU also have the characteristic of being launched running asynchronously to the CPU. So as we alluded to, for the performance, to get the performance, it is essential to avoid the extra synchronization that are characteristic to these X runtime contexts. So how can we get the performance when the performance that depend on the knowledge of these extra contexts, but we are not telling MPI, and we're not able to telling MPI about it? So before we introduce our proposal, we also would like to look at two previous attempts or previous stories that leading to our proposal. First is the endpoints proposal, which is presented in 2013, 9 years ago, but unfortunately at this point, I think it's dead. So we'll explain why it's dead. So as a synopsis, the endpoints proposal proposed to build an endpoints communicator. And in the communicator where each thread is treated as if it's a virtual process. So the good point is that once we have this communicator, this is a very small API edition, just get the API to how to create this communicator. But once we have this communicator, every older existing MPI operations that works with the communicator should be able to work with the endpoints communicator. And the application will be able to directly, explicitly addressing the thread context by using virtual ranks. On the surface, it's really good, but when we are actually working with it, the devil is in the details. So MPI with the endpoint proposal still does not acknowledge threads, right? It just pretend the threads is the same as the processes. Of course, in reality, when we're looking at the larger parts of the MPI, this is not exactly true. And for implementation, inflating the threads to virtual processes has implications to MPI semantics at large. For example, for implementations, we need what do we do when we duplicating a communicator? What do we do when we trying to get a group from the communicator and do merge, join, etc., and build up the communicator? And what do we do when these virtual processes are involved in building up intercommunicator, and joining and merge, etc. These are complications that, given that the user may not be interested, they only interested in how to get their parallel pattern to work, right? But we still need to work with the solve it, because we cannot leave like getting holes and tell applications say go around it, just work with your part. So that's for the implementation. There's a challenge to how to implement the endpoints proposal. And for the users, there's also the challenge that how to manage the endpoints virtual process mapping. Because unlike the processes, virtual process threads may not be as persistent as the processes. When we go in and out of the parallel region, threads may come and go, and so users still need to manage how to manage the mapping. So this is the complexity involved in the implementation and the usage is the first nail to the coffin of the endpoints proposal, I believe. So second nail to the coffin is the implicit solutions that currently, or as you can tell, all MPI, major MPI implementation like MPIX and OpenMPI all adopted this solution. And the nail become, because if this solution works, then we don't need an endpoint proposal. And to some degree, it does work. So with the implicit solution is built on this thesis that the MPI, even starting with the MPI1, MPI already provides sufficient means to express the parallelism. For example, communication on different communicators, or communication going from or going to different ranks, and or using different distinct tags. And let's assume no wildcard receive is being used. Then all these traffic can go completely concurrent without problem, because the outcome will not intercept. And so in theory, if the application express their parallelism, like thread concurrency, using communicators, for example, as a simplest of these cases, then implementation can explore that, and we can achieve perfect network endpoint mapping if user match their threads with, for example, communicators. And we did demonstrate that with engineered micro benchmarks. However, there's still drawbacks. The number one drawback is communicators, however, they all ranks or tags, they are kind of wrong semantics for execution context, right? Because communicator is to grouping process and grouping communication pairs, and they are not designed to express, say, this is your threads. And even though you can do that, the complication comes, for example, different library, different usage may construct multiple communicators during the process of the building up the final communicator. And when they're using third-party libraries, they often pass the communicator around. So things can happen that a single thread may use multiple communicators, for example. And we only have a limited number of finite amount of network endpoints. What if the application uses more communicators than the available endpoints? Then we will end up remapping the same different communicators onto the same network endpoints. So in reality, it's the perfect situation is rare, and we may still end up a single thread mapped to multiple endpoints, which is a waste of resource, or have multiple threads mapped onto the same network, then which means you get a miserable performance back again. And the worst thing is there's nothing. It's very difficult to educate the user about that, because this depends on your implementation internal policy. And OpenMPI and MPIX may use different policy. So one pattern works for MPIX, it may not work for OpenMPI, for example. And even when we reach the manager using a co-design manager to the perfect mapping, we may still not be able to match the performance of MPI thread single, for example. The reason is for correctness, we still need to add the logs. Even the logs are not being contended, they still add the overhead, especially for small messages. So here leads to our proposal for MPI+X stream. So our proposal directly addressed the issue we identified so far, is how to give MPI the concept of X execution context. So we using the MPI+X stream is created using MPI+X stream create. It supplies info hints, and by default we can give it info now, and basically identifies a generic CPU context, which is a thread. But we can narrow down the MPI+X stream by attaching a specific info hint. For example, give it a CUDA string T. Then the implementation, essentially, you are giving this concept to the MPI, and MPI implementation will understand, this is a offloading context, and it need to be async launched. And to use the MPI+X stream, we follow the example of the endpoints proposal. We build the communicator, we create a stream communicator. And the syntax of the MPI+X stream create is it follows the same semantics of MPI do. So you supply a parent communicator, but then in addition, you attach your local stream to it. So this communicator building is collectives. So every process is going to supply their local stream. So once you build the communicator, we not only know our own local context, we also know what is the remote context we are trying to get to. And it turns out this is critical in reaching the ideal performance. So think about it, that if we don't specify which remote context we are going to, the message is going to arrive generally. Then in order to deliver this message to the right context, some kind of inter-thread synchronization on the receiver end is unavoidable. So only by specifying both the local context and the remote context, we can directly deliver the message to the right inbox without adding any overhead. And also the benefit shares the same benefit of endpoint proposal. It's a kind of backward compatible. The existing MPI functions should work. If the existing MPI function works with the communicator, they can directly work with the stream communicator, just with added new semantics of serial. Did I mention the serial context? So MPI+X stream is required by definition in the standard that it's a serial context. It means that when user issue operations on the MPI+X stream, they need to make sure they issue those operations within a serial context, or either within the single thread, if they, or if it's necessary, they need to add locks to make sure it will they never be issued concurrently. So with that guarantee, the implementation don't need to have locks. So it's also backward compatible in the sense that the conventional communicator you can think about it as the same as the stream communicator, but it's supplied with MPI+X stream now. So if you don't supply it, it goes back to the implicit the implicit solution we talked about. It may still using multiple endpoints, but we will just do our best. So there's a few notes on using the stream communicator, which I alluded to. So existing MPI function will work, but applications, you just need to remember it's illegal to operate on a MPI+X stream concurrently. And if necessary, for example, you're running progress thread or some kind of a synchronization, use locks if necessary. So in a sense, compared to the implicit scheme, in a sense, we are shifting the burden of thread synchronization from the implementation to application. And we argue this is this way it is less complex and more effective on the application side, because as implementation, we don't know your application pattern. We cannot control your application pattern, but as an application, you can. And you know what you want to do and what your goal is. So let's shift from the MPI thread context, look at the GPU async launch scenario. So for here, we propose a set of APIs for asyncly launching the MPI communication onto the offloading context. So these API, I would call it, they are alias APIs. So if you notice, they have the exact same signature as the corresponding, for example, MPI extend enqueue has exact signature as MPI send, and they also mean the exact, have the same semantics, except have additional semantics, orthogonal semantics. Now this same operation will be asynchronously launched onto the offloading context. So even though there's a lot of new APIs being added, we can think about this as very similar to the MPI, the large count APIs added in the MPI4. So users don't really see these as a bunch of new functions. What they see it is just one single element of orthogonal addition of semantics, right? In the MPI, in the large count scenario, for example, MPI send-c, we added this large count semantics. And for these MPI extend enqueue, we added the enqueue semantics. The rest is exactly the same as what is specified in current MPI standard. So people may often surprised that we propose, for example, MPI+X send enqueue, because they understand MPI send enqueue is already an asynchronous operation, right? And in the CUDA world, that is async. So MPI send is also a non-blocking asynchronous operation. So why we propose that? Do we need that at all? So I would emphasize that actually there's two different types of async, just to clarify. MPI send non-blocking operations are asynchronous regarding to the data buffer. So whether the buffer can be reused for the receiving end, whether the data buffer is ready to consume. And the GPU async kernel launching is regarding to the launching on the GPU. So these two async models are orthogonal, and there's no reason they cannot be combined. For example, once you launch the operation onto the GPU context, we still between the kernels, it still matters. They want whether what's the dependency on the data buffer and whether they want that mode be synchronous or not. So I think we think it's orthogonal. That's why we propose all of them. So the final addition is, so far we described the stream communicator. We can informally refer them as a single stream communicator. And that works very well for the one-to-one pattern. A typical one-to-one pattern is in the stencil application that each thread only talking to a unique thread in the neighboring process. And with that, we can just dedicate each unique single communicator to each thread. Then they can just use the communicator the old way. However, there's a new different patterns that other than one-to-one pattern. For example, in what's here showing is a N-to-1 pattern that are often used in event dispatching system. Like every threads can randomly generate events, and then the single thread may receive those pull these events and deliver the dispatch the actions upon these events. And for this we still can make this pattern using the single stream communicator. But imagine on some of these threads, they may have to use multiple communicators within single thread and have to pull through the every communicators in turn. And not only this is adding extra latency to your performance, it also makes the code really complicated. So compared to rather than just dealing with one super communicator, you have to figure out which communicator for which. So for this, we propose multiplex stream communicators. So a multiplex stream communicator is constructed very similarly to a single stream communicator, but instead of us just supply a single local MPI+X stream, we supply an array of them. So this communicator will have everything, array of local contexts and array of remote contexts as well. So how to use them? To use a multiplex stream communicator, we have to propose some new API, unfortunately, and to limit the impact to the complexity, float of the standard, we limit these to a few point-to-point operations. MPIX, we call it MPIX stream send, stream receive, stream I send, stream I receive, and the regular MPI wait can use it on the non-blocking functions. So for these, if you squint your eyes, these are almost same as MPI send, except we are addressing the threads using a process plus thread index kind of a combo way. So we achieve the same objective like MPI endpoints. We can user application can directly address any of the thread contexts locally or remotely, but we are not conflating the thread into processes. So we remove the potential complications that user don't really care about it. Just let's not deal with it. Okay, so finally, let's look at the promise of performance that the MPI+X stream will bring for the MPI+THREAD. So showing three curves here. The red curve is what we already showed. The miserable one is really bad. I don't want to look at it. Then showing the green curve is the implicit solution with engineered co-designed micro benchmark. When we reach the perfect endpoints of thread mapping, we can get very good scaling. And with MPI+X stream, we get a very good scaling as well. And in addition, we get 20% even better performance than the perfect situation in the implicit solution. So not only the performance gain may be small, right? Depend on your application, what you're looking for. But what I want to note is with the implicit scheme, to reach these results, really we always need some kind of co-design, and that's not easy to get. Like in your application, you need to constantly working with your implementation team hand to hand together. But with the explicit stream, the mapping is fully achieved and controlled by the application. So that's I think it's the main point of our proposal. Finally, look at some code pattern to just get a real feel how our proposal will be used. So this is the MPI plus OpenMP example, and we create over that part we create the the streams, and we create multiple communicators, one for each thread. And when we get into the parallel region, each thread just use their dedicated communicator, and the API function, there's no change. It's exactly as if you are using the older MPI. With the benefit, now you have a performance. And this is the MPI plus CUDA example. And so very similar, we construct the stream and construct the stream communicator, but when we construct the stream, we supply the info hints. Now this becomes offloading context. And then on the right side, you see the actual usage. We achieved our goal of being able to asynchronously launch the MPI operation communication onto the stream context. And as you see, there's no stream synchronized. There's no heavy synchronized showing up here. All right, so we reached the summary. We propose a new MPI object for the MPI+X stream to represent the serial execution context. And we build a stream communicator to encapsulate those communication pairs or patterns groups. And our proposal will work with existing MPI functions with the addition of new semantics. And our proposal enables explicit optimizations from applications. And we would like to thank for very useful feedback during our development and the discussions from MPI Forum Hybrid Working Group, Intel MPI team, and the HP Cray MPI team. Thanks. Hi, we reached the question. So the question is, what is my assumptions about the concurrency for okay. Okay. So the question is, within that parallel region, what is our assumption on the concurrency? Is that the question? We still assume, because it still uses the MPI+X stream, the stream object. And if you use the stream object, you need to use that. Everything touch the stream object, you touch the serial. So that region is still serial context. You cannot concurrently construct, well, you can construct, you cannot construct, you only construct once, right? So there's no way you can concurrently construct the same objects anyway, right? But when you create a communicator, you cannot use the same stream concurrently in multiple threads. Yeah.
I have a question. Can you hear me?
Go ahead, Rolf.
Okay. When I would do exactly the same by creating an array of normal communicators.
Okay.
And I would use exactly the same program with MPI single thread, and I would have additional info key on these communicators telling that several threads may call MPI at the same time, but no two threads on the same communicator. Because that's what's here. No two threads on the same communicator call at the same time the MPI send and receive on that communicator. Or is there more than that functionality?
Not exactly thread single, right? With thread single, you cannot have threads ever, right? So, but we are saying if you're using MPI stream, the same stream only can be used in a serial fashion. In thread serialized.
The same stream you are using in a serial fashion. That's true.
Ralph, you may get confused because there's a talk after Zoom as well. Okay, I'm trying to understand. So your goal is trying to achieve that to be able to construct the communicator concurrently within each thread. Is that the goal here?
Okay. Okay, I think again about. Let's continue with other questions. Does it work? Yes.
So, Hui, I don't know if there is any question. I have a question. Can I do it?
Okay, Maria, go ahead.
Yeah. So what you are trying to do is, I mean, the amount of parallelism that you have on the communication will depend on how many endpoints, I don't know how you were calling that, you have on the network, right?
Right.
So now if you have an application where, imagine that I have many cores, right? But my communication endpoints is limited. You are passing the burden to the application, right? To kind of synchronize those either streams or threads to kind of distribute those network endpoints among them, right? Because so that's part of the trade. That's also a trade-off here, right? If we were able to have a one-to-one mapping,
right,
this is probably not a big deal. But if we don't have that, you know, that log that it is there on the library, right? But that you want to completely remove.
So there's one note that I kind of omitted, right? In order for applications to have full control, they need to have kind of feedback that my stream really are mapped to the real endpoints. Because if they promise the same pattern may work or may not work, depending on your system. So that's one semantic is that we want to add is that when we call MPI+X stream create, it may fail. And it will succeed when we have preserved endpoints that we can give to you. And if we don't have enough endpoints, at that point it will fail. Then you can do the application can rewrite and do whatever fallback solution is.